All right. So in this chapter, content that kind of just extends some ways that we're able to solve. Um, sorry. Oh, okay. Um, in this content, we're just trying to take the algebra kind of way of solving equations and combine that with the trig practices of solving equations. So in algebra, we would have something like 3x minus 2 is equal to 1, and you would be told to solve for x. Well, now we're going to combine this with our ideas from trig and say 3 times sine of theta minus 2 is equal to 1, and we can try and solve for theta. Well, we can add 2 to both sides to get 3 sine of theta is equal to 1 plus 2 is 3. So I divide both sides by 3 to get sine of theta is equal to 1. Well, this has a solution for theta. If we look at the unit circle, where is sine equal to 1? And sine is our y value. So we look around there and we see one value on our unit circle from 0 to 2 pi, and that is pi over 2. But is pi over 2 the only answer? Well, the idea is really just there was just one answer there from looking at the unit circle, but that's because we're only showing stuff angles between 0 and 2 pi. Really, we only care about this spot on the unit circle for this output. So everything that is coterminal to pi over 2 is going to be an answer. So I can add 2 pi, and that's another answer. I can add 2 pi again and again, or subtract 2 pi again and again. So we can represent all possible answers here by saying it's pi over 2 plus 2 pi times k for some integer k. Now, typically, these questions actually give us a restricted domain. So the most common one that we'll see for this kind of stuff is that theta is between 0 and 2 pi. I do that very poorly. 0 and 2 pi. So where is this true on the domain from 0 to 2 pi? Well, that's just our normal answer, a regular pi over 2. So if I ask this question to solve for theta here, where theta is between 0 and 2 pi, then our answer would be pi over 2. And it would just be one answer there. Now, what if things looked a little bit different? So this gave us one specific answer, but in general, that may not be the case. So consider instead a question like sine of theta 2 times sine of theta is equal to the square root of 2. Well, we can maybe immediately see what I'm getting at here. We divide both sides by 2 and get that sine of theta is root 2 over 2. So let's ask ourselves, where is sine equal to root 2 over 2? And I forgot to write it, but I really meant to just restrict theta from 0 to 2 pi. So where on the unit circle is sine equal to root 2 over 2? Now, I know immediately that there are going to be two answers to this. Why? Well, if we look at our unit circle, we are trying to see where the y value is root 2 over 2. So if I draw this line, y equals root 2 over 2. Then I am going to intersect the unit circle at 2 coordinates, at 2 distinct angles. So we need to figure out which 2 angles from 0 to 2 pi give sine and output of root 2 over 2. Now the first one would be pi over 4, the one in the first quadrant, and the one in the second quadrant, I believe is 3 pi over 4. So generally, a lot of the times, unless our answers turn out to be weird numbers like 1, like up here with this coordinate 0, 1, or if our, yeah, 1, or if we would have been -1, that's really the only case where we only had one solution in a full period. Now, it could have been the case where what if instead I gave you a different domain? Only give me answers from 0 to pi over 2. Well, we can think of that as only answers in the first quadrant. So if I restrict myself to just being between 0 and pi over 2, then yeah, my answer should be pi over 4. So we really do need to pay attention to what quadrant we're being told that we're in, because that changes what our answers look like, where our answers are, and how we need to adjust for that as well. Now, let's say, again, we have the same question, but I restricted my domain from 2 pi to 4 pi. Well, these are my answers from the first period. How do I take these numbers and move them forward into this next period? I can just add 2 pi to each of them, right? To find coterminal angles that are just one period forward. So if I was given this question, my answers would be pi over 4 plus 2 pi, 3 pi over 4 plus 2 pi. And those are my answers. So generally speaking, starting with, the trig functions looking like this, things really aren't too bad. We can always just, if we have some linear thing here, I think we're pretty good at solving for sine there. So the approach is just to start with this algebraic expression, you rewrite it to solve for sine of theta, and then once you have this, you use the information available to you to figure out what theta has to be. And that is essentially looking at the unit circle. Very good. Well, now we can take it up a notch. And I said before, just now, that that's our approach for linear equations. But what if our equation is not linear? What if I have something like sine of theta squared? Let me think carefully about how I want to do this. Plus five sine of theta plus 6 is equal to 0. Now, as before, when we solved for sine, it was almost like we were just solving for any other variable that we were used to doing. So let's replace sine of theta with just x. And this turns into x squared plus 5x plus 6 is equal to 0. And do we remember a good portion of an algebra class devoted to figuring out the roots of a polynomial or the solution to this equation? And I hope we do. And that is a few different approaches that we have available to us. Now, generally, the one that always works is the quadratic formula. If we remember minus b plus or minus the square root of b squared minus 4 times a times c all over 2 times a gives us both of our potential solutions. But sometimes, like hopefully here, we can actually factor our expression out instead. So there's just a 1 right here for the coefficient, so I don't need to worry anything out front. Now everything is positive, so both of these terms here I think are going to be positive values. Now the term here and the term here get multiplied together to give me the 6, but they will add together to give me the 5. So what are the factors of 6? Well, I have 1 and 6. Those add together to give me 7. Or I have 2 and 3, which add together to give me 5. So this factors to x plus 2 times x plus 3. Perfect. So if I'm wanting solutions to this thing being 0, then really I want this part to be 0 or this part to be 0. So it's not that our solutions are 2 and 3. In this case, x is negative 2 and negative 3 are both of our solutions. Well, here, I did all this work in terms of x, which is perfectly fine if I want to make that substitution. But really, I'm not solving for x. I'm solving for something with sine of theta. So really, what I have here is that sine of theta is equal to 2, and sine of theta is equal to 3. So now I want to solve for when sine of theta is 2, and find the solutions for when sine of theta is 3. Well, it turns out sine of theta is never going to be equal to 2 and never going to be equal to 3 for the same reason, which maybe look at our unit circle to remember this. If we want our y value to be 2, well, this y value is 1, and 2 is all the way up here. And how many times does this intersect the unit circle? 0. And even worse for 3, if it's all the way up here, then how many times does that line intersect the unit circle? 0. Why? Because the biggest output for sine or cosine, the maximum value, is 1. And the minimum value is -1. I'm so sorry. I just realized that I made this really big emphasis about the answer for this to be x is -2 and x is -3. And then I just wrote down +2 and +3 there. But the exact same thing happens. When is sine -2? Never. When is sine -3? Never. Because the smallest that sine can be is -1. So what do we say for theta? Really concerned and confused now. We say no solutions. You can even say D and E for does not exist. Whatever you want to communicate to say there are no solutions. The solutions don't exist. You can't solve this. Very good. Now, if it turned out that magically everything that happened up here was different in some way, where maybe we did have solutions. So let's say instead something was different so that our two solutions were something like the square root of 2 over 2 and 1/2. This is entirely possible. Now, we probably wouldn't get root 2 over 2 from factoring, but if we use a quadratic formula, that is a very normal number to pop out of the quadratic formula. So now if we somehow got that x was root 2 over 2 and x is 1/2, then we are solving x is root 2 over 2. Sorry, sine is root 2 over 2 and solving for sine is 1/2. We do both of these. And now I didn't specify yet, but let's find solutions for when theta is between 0 and 2 pi. So now when is sine root 2 over 2 in our domain? And if we remember from a previous question just a minute ago, we got pi over 4 and 3 pi over 4. Now when is sine 1/2 in our domain? That happens at pi over 6 and 5 pi over 6. So how many solutions are there? Well, I am okay with sine being this or being this. It does not have to be both. So as long as I'm root 2 over 2 or I'm 1/2, then this works. Then we're good, which means that all 4 of these numbers that I found are correct answers. So my solutions would be theta is pi over 4, 3 pi over 4, pi over 6, and 5 pi over 6. Perfect. So that is how we approach our quadratic equations. And again, in the world where we can't factor it, where we look at that and we think, I am just not sure what 2 numbers I could possibly pull out of those to factor, then we always can fall back on that quadratic formula. Very good. So now I'm going to actually split this into 2 parts just to illustrate something. So there was an example in class that I very much got stuck on. And the way that I was afraid we'd have to do it, it turns out exactly is the way that we do it. So I'll post that in a second video so that those that only want to see that can get to skip all the rest of this, I guess. But anyway, so that is the bulk of this chapter. And the niche messed up part is going to be this next video that I'm about to post. So part 2, I guess.